Hello. My name is Carter, and I'll be going over some differential equations review with like a weed whacker in the background. So I'm sorry about that. I actually recorded this once, and then the video kind of like froze for the entirety of it. So I'm gonna be essentially just going through this I took, and I'll be talking through it again. So maybe this is for the best. Maybe be a little more concise. Um, but yeah, so we're just gonna review differential equations for the test, and that's about it. So we'll start with the most obvious, which is first order differential differential equations. Awesome. So what we have is that we have the general formula that dy by dx is equal to f of x comma y. And our objective here is we want to calculate the function y given an initial condition. And obviously, that's going to satisfy this differential equation we just laid out, given some initial condition. There we go. So we're going to do a really basic problem that was featured in the notes. We're going to say that dy by dx is equal to simply just x, and then y of 1 is equal to 2. And for this, we're actually going to use two methods, just to cover all the bases. So yeah, let's just do that first. So the first one, we start with a simple separation of variables. So we have dy is equal to x dx. So we're going to integrate that. This is an indefinite integral, x dx, and then we actually do the integration. We say y is equal to x squared over 2 plus c. And simple reverse power rule. I don't know if it has a more formal name than that. But again, we don't want to keep it in terms of c. We have an initial condition, so I'll have to use that. We're just going to plug in our values. X equals 1, y equals 2. So we're going to say 2 is equal to 1/2 plus c. Thus, c is equal to 3/2. And that was really simple. Obviously, that was like a really simple problem. But that is the gist of it. I just want to showcase these two methods for review. Now we have method 2. I prefer this method. It's, we can essentially divide this into two steps. We find we find the equation, and then we find c. And then I guess we can also rewrite the equation. And I feel like, I'm not saying it's hard. I'm just saying this one might be a little easier. So we're going to start, and we're going to do our separated variables again. And now we're going to take our integral, but this is where the difference occurs. Instead of an indefinite one, which will give us a c value, we're going to take a definite integral given an initial condition. So obviously, this is our y side per se, and we're going to essentially use the y variable here. So we're going to go from 2 to y. This is our initial condition, 2, and y is the variable in use here. And similarly, we're going to do 1 to x. So I hope you see the connections between our initial our initial condition and the definite integral here. Now we're going to integrate, say this is equal to this, and obviously now we don't need a c, which is nice. And we will finish our integral up, so x squared over 2 minus 1/2, and what you're going to see is we do get the exact same thing. And again, I like this one because while here I kind of showed, we have like 3 different movements, 3 different steps. This one's all just kind of like one fluid motion. So for me, that helps a lot. I like that. And while we're here, I mean, we can go over one of the verify problems from the notes. I kind of liked it. It was interesting, and I feel like it's a cool concept we should know. So I'm going to go from 1 to x. I'm not even going to try to say it, honestly. I don't want to stutter much. X squared y prime plus xy equals x e to the x. Okay. So what we have here is we want to verify something. Or to verify something, we need to, prove that that expression is equal to e to the x. This thing right here. And what you're going to notice is we have an x, we have a y, and we have a y prime. So we know what y is. And, We don't really care what x is because our final answer should be in terms of x. But we don't know what y prime is. So just the first thing we're going to do is solve for y prime. And it's going to be a little long-winded, so buckle in. What we see is we actually have two terms here, so we're going to have to use the product rule. And we're going to take first the derivative of 1 over x, which is going to be negative 1 over x squared, times the integral of 1 to x e to the t dt. There we go. And plus, now we don't take the derivative of 1 over x, we leave that as is, but we take the derivative of this integral, and that's just going to be the fundamental theory of calculus, theorem of calculus, which means we're just going to have e to the x over x, which is nice. Now, since we know what y prime is, we're going to substitute these values in. So we're just going to rewrite the equation here. E to the x, and then we're going to substitute things in. So x squared, and then we have negative 1 over x squared, integral from 1 to x, e to the t over t dt, plus 1 over x, e to the x, x. Okay. Well, let's clear it on it. X times y, and don't know why I'm faltering over here. We need to plug in our values for y, which is 1 over x, integral from 1 to x, e to the t over t dt equals x, e to the x. There we go. Okay, that was a mouthful, but this x is actually, it's intimidating, but it's actually some easy simplification. So if we were to distribute this x squared here to here, it's just nice cancel. So we're just going to be left with the negative integral from 1 to x, e to the t over t dt. Now, if we were going to distribute to the other side, first we can see that, you can't see anything yet. I don't know why I said that. Essentially, we can see that, I don't know why I'm stuttering all the time. Okay. Essentially, it's going to cancel out, and we're going to have just an e to the x. Hopefully you can see that. Now on this side, x obviously cancels out with 1 over x, and you're just going to be left with the integral from 1 to x, e to the t over t dt. And now we want to say that this equals e to the x, and what we can see is that these just cancel out, and we're left with e to the x is equal to e to the x, which means QED, black box, we're good. Okay, that was it. Now we can also say, I think an important thing to note is, pertains to radioactivity, but it's a general idea. We say that dA by dt is proportional to A, and just kind of, I don't know if this will be on this test exactly, but kind of just note that just in case. This is a proportionality sign. And from this, we can come to the conclusion that the differential equation is equal to negative lambda A. Negative lambda is a constant. For radioactivity, you just use lambda. I mean, hypothetically, you can walk in with any constant, any variable, but negative lambda is what we use here. And I'll just write the radioactivity formula, which is A equals A sub 0 e to the negative lambda t. And then you can also deduce lambda from that, but we're not going to do that. Don't know why I'm getting so many calls all of a sudden. Okay. Is there anything else I want? Oh yeah. So also in the notes we talk about temperature. We about the cooling. In terms of just regular stuff. I don't know. I'm getting a little distracted now. 1 second. Okay. Now we'll just quickly talk about slope fields. They're kind of lame, but we'll just do that. So in the notes we go over dy by dx is equal to x. Now for this, essentially, I'll write our key for us. So you just got to keep this in mind for the test. If it's 0, it's a dot. If it's plus 1, we have a sloped line like this. If it's minus 1, we have a reverse slope line. Plus 2, it's still up like plus 1, but now it's like slightly steeper. Minus 2, slightly steeper, but in the opposite direction. Simple. And I'll move this down here. Okay, I'll rewrite this. Okay, so it's really ugly, but at 0, 0, our differential equation is simply going to be 0. It's actually going to be 0 for all these points right here because x is equal to 0. Then over here, we're going to have this and that, and hopefully you can fill that in. It's not the most complicated process. Now we have Euler's method. Euler's method is pretty simple, but let us go over it nonetheless. Okay, so we're just going to jump right into a problem, and then I'll give you the generalized formula. So we're just going to say this, and then our initial condition, y of 1 equals 2, and then we want to find y of 2 in 2 steps. So we did do this one in the notes, but I'll go over it. So the first thing you want to do with Euler's method is you're going to want to lay out the variables, and you're going to want to do this for each step. So you see that we're going to have 2 steps, and essentially, you see the way I think about it is like we have a jump, and it's a distance of 1. So 1 divided by 2, we're going to move a distance of 0.5 each iteration. So our first variable is going to be x sub 0, and that's going to be equal to 1. Y sub 0 is going to be equal to 2. And our differential equation in terms of x sub 0 and y sub 0 is equal just to 1. You plug in x equals 1 into the square root of x, and you're going to get 1. Now our Euler's method equation, y1 is equal to y sub 0 plus our differential. And then you can write it as like dx. You can, I think it's written by Kanuga as x1 minus x sub 0. In this case, our x sub 1 is going to be 1.5, and our x sub 0 is going to be 1. So you're going to get 0.5. And then we could say y1 is equal to 2 plus our 1 times 0.5, which is equal to 2.5. And essentially, this was our step 1. So then we would have to do step 2. And that's going to actually lead us to our answer, but I'm not going to do that because it's the same process. Essentially, you lay out the variables, plug it into this formula once again, and that is that. So we're going to go on to our last part of this video, autonomous. I did not spell that right. I don't know how to spell. Hopefully that's right. Equations. Now, this is probably one of the most difficult parts, maybe, I don't know. We have our generalized formula as dy by dx is equal to f of y, and if we're going to just scroll all the way up, we're going to see that this is in terms of x and y. Autonomous is just in terms of y. Also, I should have noticed earlier, that was our first order differential equation. You can go to your nth order differential equation, but we don't really do that in this class, so we're not going to right now. Back to autonomous, essentially it's just in terms of y. So if we have an example of dA by dt, should be familiar, it's our radioactivity differential. This will be autonomous, it's only in terms of A. You might be like, oh, what's this then? Well, that's our constant, it's not x, so we're fine. Now, we're going to have our dy by dx, and we're going to say this is equal to x plus y, and just write that a little better. We're going to see that there's an x in here, and just because of that, because it's an x and it's not simply in terms of y, it will be not autonomous. Now, I think probably the most important part of this whole autonomous chapter are our like logistic equation problems. So, I mean, I kind of recommend, looking in the notes and just making sure you understand it, but I'll go over kind of how I think about it briefly. So, essentially, you have 3 generalized cases that don't change. Like you're essentially going to be given a differential equation, you're going to be given an initial condition, and you're going to be asked a few questions. And your answers to these questions are going to be like one of 3 possible answers, and you have to determine which case it is. So, an answer we're gonna probably be asked is the limit as t approaches infinity, p of t. So that would be our plain function. Then we're going to have our limit as t approaches infinity, p prime of t, and that is our derivative as t approaches infinity. And then also, when is p prime of t greatest? And I feel like those are the main questions. So that's just what we're going to talk about now. So what we're going to do is what we need to know is our m over 2 value, which is our midpoint sort of thing, and our m. This is like the key. And clearly, you might just be able to see here, we have kind of three cases, and those happen to be the exact cases that we're going to talk about. So the first case would be when our initial value is less than m over 2. So when this is the case, p prime of t, I'm just going to get this ready, is greatest at, and I won't finish that in, but essentially what we have is we're going to say we start right here, where it's going to be sloping upwards, and back to decreasing. And you might be able to tell just from the graph, it's greatest right here when p is equal to m over 2. So if you ever see an initial condition less than m over 2, the derivative is going to be greatest at that, kind of like the halfway point sort of thing. Now let us talk about, I'm just going to copy this. I feel like that might be easier. I don't know. Now it's when m sub 0 is here. Okay. M sub 0 is greater than m over 2, but less than m. Then we have to say when is it greatest. So our curve now is going to simply look like this. So we're going to have our initial value here per se, and then we're going to go and it curves like that. And what you can determine is that our highest value is simply going to be at t equals 0. Pretty straightforward. And for the last thing, when m sub 0 is greater than m, p prime of t is greatest at, let me draw the curve, of course, and essentially it's just like this. And spoiler, it's going to be at t equals 0 again. So I mean, that's the gist. Okay. Just also say that the limit as t approaches infinity, p of t, what you can see is that no matter what case, 1, 2, or 3, our function is always going to approach that m. So no matter what, this approaches our m value. Now, our limit as t approaches infinity of p prime of t, well, our derivative is always decreasing. Our slope is always decreasing. So it's always going to approach 0. And so that, I don't know, I guess that's kind of like easy. You don't have to really worry about anything. So there actually are a lot of similarities here. Like, clearly these two are the same. These are the same for everything, and then that one's just different. But I mean, it's not horrible. You kind of just have to pay attention to these cases. I'd recommend looking at the notes and give them a better explanation. I'm kind of rushing right here to make it brief. But I don't know. That's kind of the gist. I hope this helped in some capacity. And I mean, good luck on the test. I'll see you later.